Hello, everyone. Good afternoon. Welcome to our weekly M-Cubed seminar. Today is being given virtually, coming from England. Today our speaker is Irina Sandu from the ECMWF. Irina is the science lead for the Destination Earth activity, about which you'll hear more in a minute or two. Our research areas include boundary layer clouds and their spatiotemporal distribution, aerosol cloud interactions, and turbulent diffusion stable conditions, orographic drag, and land atmospheric coupling. Irina has used a variety of models, from idealized theoretical models to LES to mesoscale and global NWP models, and a wide range of data sets to address questions ranging from the process understanding to aspects of subgrid parameterizations and model evaluation. Today, the seminar is entitled Destination Earth, Digital Twins of the Earth System. Irina, the screen is yours.
Hello, thank you. Thanks for the invitation. I'm stepping in for Peter Bauer, who couldn't be here today. Thanks, Rich, for the introduction. Indeed, I was leading the physics team at the European Center for Medium Range Weather Forecast for several years. And last year, I took on a new role as we started our involvement at ECMWF in the Destination Earth program of the European Union. So I'm going to give today an overview of what Destination Earth is, where are we today, a little bit more than 1 year into the program, and I will particularly focus on our role at ECMWF in developing the digital twins of Destination Earth and the digital twin engine, and I'll talk about that more in detail. And this, of course, it's a huge collaborative effort, not only at ECMWF, and you see many names there from ECMWF. Some of you may recognize quite a few of the names, but we also had quite a large group of people actually who joined us in this initiative during last year, but it's also a collaborative effort with many colleagues from the member states of ECMWF. So with that, I will start, and I will start by, if my screen wants to advance, sorry, by saying what is Destination Earth. It's an initiative of the European Union in the support of its Green Deal. And the aim is really to build a digital twin of the Earth, a replica, a highly detailed replica of the Earth system, obtained by fusioning simulations at very high resolution towards kilometer scale with observations based on taking advantage of the advances in supercomputing in Europe in particular, and of the incoming new facilities that I will touch upon, which are called the Euro HPC, which are the pre-exascale machines in Europe. So Destination Earth, this initiative of the European Commission is really in several phases. We are now in the first phase, which started end of 2021, and it will be until mid-24. Then there will be several phases. We are in discussions with the European Commission about these next phases. The initiative is implemented by 3 entities: the European Center for Medium Range Weather Forecast, where I work, the European Space Agency, ESA, and EUMETSAT. And the key elements of the who are in charge of developing the key elements of the program, which aims to build this digital twin of the Earth. And the key elements are the digital twin engine, and I'll describe that in a minute, and the digital twins. This is our role at ECMWF. The data lake, which contains all the data from the digital twins, but also our other sources of data, for example, from satellites, and in particular the Copernicus satellites, for example. That's under the responsibility of EUMETSAT. And finally, what we call the core platform, through which the users can interact with this digital replica of the Earth in order to study different parts of the atmosphere, ocean, sea ice, land, etc., in support of better adapting to climate change and to better responding to the dangers posed by extreme events in particular. So the core platform is developed by the European Space Agency. And we are really working, the three entities are really working together for implementing this program in collaboration with many partners across Europe. What are the digital twins in Destination Earth? Are they just NWP on steroids? I would say no. For me, there are three key elements of the digital twins. The first one that comes into mind, and that's what people think of a lot when are talking about digital twins of the Earth, it's a better simulation based on higher resolution, more realistic models, going in terms of Earth system modeling to kilometer scale, the ultra high, what we call also the global ultra high resolution Earth system models. And there are many efforts across the world doing that, but that's just one component. The second component is really an effort of better combining all the observed and simulated information from the entire Earth system, both the physical system and the impact sector systems like food, water, energy, health, in the aim of better supporting action scenarios in response to the dangers posed by extreme events and climate change. And the third component, which is really important and complements in a way what it's there already in terms of prediction capabilities, is an interactive and configurable access to all data models and workflows. So what is the aim really? The aim is to produce more realistic information both at global scale and at local scale. And you can see here simulations from a European project called NextGEMS that I will describe in a minute. It's a research project that Björn Stevens at the Max Planck Institute and I at ECMWF are co-leading, which aims to develop what we call storm and eddy resolving simulations. And you can see here simulations. These are the wind gusts at 4 kilometers with the IFS, and this is the sea ice, and you can see beautiful sea ice cracks with the FESOM model from the Alfred Wegener Institute at the resolution around 4 or 5 kilometers in the Arctic as well. But it's going beyond that. It's going beyond this kilometer scale in the atmosphere and the ocean. It's also going towards including impact sector elements like hydrology, for example. You can see here the river discharge at 10 kilometer. And the idea is to also bring this into the same prediction system, this type of impact sector like hydrology, like air quality. Finally, the aim is to build this interactive system, and this is of course not something we are going to do in the first 2 years, but this is the long-term vision in Destination Earth, so that users can trial different scenarios in support of adaptation and mitigation actions. Now, the Destination Earth digital twins, of course, they build on the technology advances, the advances in the digital continuum in the last years, and the increased supercomputing facilities in particular, going towards pre-exascale and soon towards exascale. But they also build the fact that we can even envisage to run simulations at these scales. It's only thanks to the investments in adapting our codes to this new generation of mixed architectures. And in particular at ECMWF, in collaboration with many colleagues from our member and cooperating states, there was a program called the Scalability Program over the last 10 years or so, which really invested in trying to make the first step towards being able to even run this new generation of supercomputers. We are not there yet. There is a lot of work to be done as well to complete the digital revolution of Earth system science. And there is this very nice paper by Peter Bauer and colleagues which describes these efforts. And this is also something that Destination Earth is going to contribute to, really trying to find solutions to run efficiently, interoperably on these supercomputers in terms of numerical methods, of algorithms, of data structures, of programming models, but also in bringing in more and more machine learning elements into the workflow. And in short, it's an investment to make sure that the technology is not running away from us and that we can really use the world's mightiest computers for improving our prediction capabilities in Europe and beyond. Now, just a few words on EuroHPC, because in Destination Earth, we are going to use these supercomputers to produce the digital twins. It's an 8 billion program in Europe towards exascale, and there are already 3 large supercomputers of the order of hundreds of petaflops, which are being installed in Finland, Italy, and Spain. The one in Finland is already in operation since September. I mean, there are still tests ongoing, there are still issues, but we can already start trying to adapt our codes for this supercomputers. There will be one in Italy and there will be one in Spain. So one in Bologna, one in Barcelona, and then there are 5 smaller ones. And by 2024, there should be 2 high-end of around 1,000 petaflops supercomputers. One will be in Jülich. And from this, 10% of the European Union's access time is dedicated to strategic initiatives like Destination Earth, and Destination Earth can use up to 5% for now from these resources for powering its digital twins. Of course, Destination Earth digital twins are also built on increasing consensus. And as you very well know, and there are many efforts in this direction in the US as well, many in Japan, also Australia. There are activities everywhere to go towards digital twins. There is the WCRP Lighthouse activity called Digital Earth, where there is an effort which is pulling together the efforts in the community to, on one hand, develop the high resolution coupled global modeling facilities, but also combining that with regional systems at even higher resolution, while making an effort to adapt our weather and climate codes to the new generation of supercomputers, and of course to evaluate using observations the quality of this new type of prediction systems, new generation of prediction systems. Destination Earth also builds on existing services enormously. It's a very strong, and for Destination Earth to be successful, it has to work in a very close synergy with the services, science, and technology in Europe and beyond. It builds, of course, on decades of advancements in numerical weather and climate prediction, and on the quiet revolution of numerical weather prediction in particular, at the heart of which is this fusion of simulation and observations, which is taken to another scale in the framework of Destination Earth at these unprecedented high resolutions. But of course, it builds as well on the Earth system and impact science, because it has to bring together a new it relies on a new generation of Earth system models, which are just being developed. And it relies, as I was saying, on the technology and infrastructures, and for Destination in particular, on the EuroHPC facilities. And the aim really of Destination Earth is to complement our European capability, to complement and augment our European capability to monitor and predict our changing Earth by by complementing existing national and European efforts, such as those provided, for example, by the National Met Services and the Copernicus Services, which is a European initiative. So now I will talk a bit more, after this more general introduction, I'll talk more particular about our role at ECMWF in this initiative, which really builds on the decades of expertise in numerical weather prediction in terms of both modeling and use of observations through data assimilation, but also in super computing and data handling. So we are responsible in the phase 1 to deliver the digital twin engine, which it's really a common approach for a unified orchestration of the Earth system simulations and their fusion with the observations based on these large-scale supercomputing facilities and data handling resources. We are also responsible to deliver the first high-priority digital twins, the first 2 digital twins in destination Earth. One is on weather-induced and extremes. That's what we call in short the extremes digital twin, which really searches to augment our capabilities and services for the assessment of and prediction of environmental extremes based on kilometer scale global modeling, modeling at a kilometer scale globally, and sub-kilometer scale regionally, on time scales of a few days ahead. That's the first digital twin. The second digital twin is also based on kilometer scale global modeling in support of climate change adaptation policies and mitigation scenario on the long term again. Of course, we cannot achieve this just in the first phase. And it's focusing on multi-decadal timescales. And I'll go a bit more in detail about each of the twins a bit later. But first, I want to talk a little bit about the scientific vision behind Destiny's extremes and climate digital twins. And it's really not a vision which is only in Destination Earth, but it's contributed to a global vision towards which many of the centers are going, and which is going on one hand towards enhancing the convergence of weather and climate prediction systems in terms of the numerical prediction systems which are used, which share more and more already, but the idea is to bring them to share even more a common infrastructure, a similar way of using observations for initialization and for model assessment. And in terms of resolution, so bridging, and I will explain at the end why I think is really important, this bridging this gap in terms of resolutions can help us develop these systems in a better way. And I'll go into that at the end. The second really important component in my point of view is going away from this type of Earth system cascade, where the Earth system model gives some input to the impact sector models like hydrology, pollution, which are run on the side afterwards once the Earth system model run. So it's really going from that to an integrated system where the Earth system modeling and impact sector modeling are in the same workflow, and ideally where it makes sense they interact in 2 ways. And another effort in what regards the impact sectors is really a desire to strengthen the co-design aspect of this modeling system with the users from the different sectors all along. And that is why we are having strong partnerships, strong targeted user partnerships from the beginning to build the digital twins with users from different sectors like renewable energy, like floods, like wildfires, like river discharge or air quality. Because I think it's really important, especially in the light of all the high volume of data that these twins will provide, and I'm coming to that in a second, is really important to be able to tailor, and this is one of the strong points of Destination Earth, that it aims to help the users tailor the output of the digital twins to their needs. And I'll come back to this in a minute. However, There are also challenges involved with the digital twins, of course, and I'll come back at the end of the science challenges, but there are technology challenges. As I was saying a minute earlier, there are still many challenges to be able to even run our codes on these supercomputers in an optimal and efficient way and make use of the advances in supercomputing. But there will also be, of course, a data deluge. And this is a nice slide Niels Vedi put together where you can see the number of points, right? This is what we produce today in our 9-kilometer, 10-day forecasts for one deterministic run. In the beginning of, well, soon this summer, we should have an ensemble of 50 members and 9 kilometers. But for one member, already today, we produced 9 billion points, or about 100 tera per day. If we go in destination Earth up to 1 kilometer, TCO 7999, it's 1.4 kilometer about, that is 345 billion points. That's 1 petabyte per day. So there are technological challenges in order to run the twins efficiently, but there are also technological challenges in order to make use of these huge volumes of data. And that's why we have the concept of digital twin engine, which is really this unified, this software infrastructure needed for powering the digital twins. And the idea is to construct all, to build the different elements which are needed in the workflow to run these twins to efficiently on and interoperably on different supercomputing facilities, but also to run that it doesn't matter to run the twins in a similar way, so that it doesn't matter if it's a weather or climate twin, we can use we can run them and we can handle the data in similar ways. And there are different components that we are developing of the digital twin. There's of course an effort to continue the HPC adaptation and the optimization on these mixed architectures. There are still a lot of there are loads of challenges ahead with adapting for GPUs in particular. There is also a huge focus on the I/O, input, output, and data workflows, but also all the software management and the controlling the workflows. And then there's a whole visualization. How do we visualize the data, where the data sits, how do we interact with it? And Niels likes to say that you can think of a game engine type framework, but for Earth system, where you can have a collection of APIs and services, and there is a long list here that I'm not going to go into detail of software that allows to not only to run the twins, to control their flow, but also to make use of the data. And there are a few ideas which I think would advance, if we manage to advance in this direction, will advance our prediction capabilities quite significantly. So this diagram, it's a little bit complicated. You don't need to read all what is written there, but the idea is that digital twins run on the Euro HPC. That's the Euro HPC box. And then there is the data lake where the data which is saved sits. But the idea is really to bring the users to the data as much as possible. So go away from a concept where we bring, we take the model runs, we have the data, and then we put it somewhere, and then we download it, the user downloads it on his computer. Is really to go away from that and to go to workflows in which the user can configure the model, the observations, in which the data handling architectures become scalable, and selected users can really run their applications where the data is produced and accessing the data not from the disk, not from Mars. You know, we have Mars at TCMWF is our archiving system. So really not going to Mars and requesting in each individual bit of data, but listening to the data stream as it's produced. Imagine an application which, for example, for an urban application, somebody who wants to do run a urban model for New York, for the climate change, and it needs profile information from the climate run every hour. Of course, today it can't have access to that because the data from the climate models, it's at best saved on a monthly or daily basis, and it's saved at selected levels. If we manage to put into practice this data streaming concept, where you can plug in the urban model onto the climate twin, which runs and reads the data from the memory as it's produced, it's like you're listening to observations in a way. You listen, the idea is for the applications to be able to listen to the full 4D data stream on the fly as the climate simulations are produced. And if we produce these simulations regularly, not every 7 years, not like it's done now in CIMIP, but if you would produce the simulations every year or so, or every 6 months, then you can, even if the application lost the chance to couple to the climate twin, it can do that later on. It has a chance to do that next time around. And how the digital twins will be run, the idea is to produce them either in a continuous mode, like we do today in weather forecasts. For example, run the extremes twin, say once a day, and then run the climate twin every year or so. Or an on-demand mode where selected users again can demand certain type of application, certain types of simulations, or run selected periods from restart files, for example. Now, a few more details about the digital twins themselves. So I was saying there is extreme digital twin, and it has two components. It has what we call a global continuous component. That's a bit like the weather forecasts we do today at ECMWF, but do this at increased resolution, using using higher resolution observations, but also higher resolution initial conditions eventually. What we have been doing, and this is what we are doing ourselves at ECMWF, we hired quite a large number of scientists last year to focus on this effort together with our core scientists. Of course, this is an effort which goes in the same direction. It's very strongly aligned with the strategy of going towards global kilometer scale modeling at ECMWF. And what we have been doing so far, we selected an initial set of extreme event cases. We selected about 20 cases, and we ran for the first time systematically the IFS for global forecast 5 days ahead at 4.5 kilometers, and we compared them with simulations at 9 and 29. And the idea is to do this later with 3 kilometers and 1.5, and in the framework of Destination Earth, the idea is to do this on a continuous basis a few times a week and later daily. But for now, we are at this preliminary 4.5 kilometer runs. We also have done continuous periods where we run, for example, like we run when we put together a new cycle in NWP, where we run 2 months of summer, 2 months of winter with a daily 10-day forecast at 4.5 kilometer and 9 kilometer, which is our global operational high resolution forecasts. And we compare this for the first time in a systematic manner. What have we found? Well, for now, we found what we were hoping to find, but we also found surprises, which I'll tell you later about. We looked whether the first things that you think that you would improve when you improve resolution, we can see those signatures, and luckily you see that. That's good. You can see that here it's a storm. You can see the 24-hour accumulated precipitation at 29, 9, and 4.5 kilometer. And compared to observations, there is much more detail. The precipitation, it's higher at high resolution, and then especially where over orography and in low region, and low, particular over low orography, you see the benefit of the 4.5 kilometer simulation, although there are errors which are related in the where the precipitation is located. Of course, this is just one ensemble member. Ideally, you would want to do this in an ensemble, but also in this case, there was an error in the wind field. Again, medicanes, tropical cyclones, you also see a benefit as you would expect. You can see here a medicane which hit Greece in 2018, medicane Janos, which is quite studied in Europe, obviously. And you can see again that the system is deeper, the size of the system is bigger. This is the surface wind speed. It's more comparable to ASCAT, but you can also see a nice benefit in terms of waves. This is the significant wave height from the altimeter on the y-axis and the model on the x-axis, and these little crosses here show the quantiles, and you can see that at 4.5 kilometers you can see a nice benefit. Of course, again, this is one case study. We looked across several case studies where this is the case. It seems to be quite consistent. Interestingly, it seems to come from the increase in high resolution atmospheric resolution, not in the increase in the wave model resolution. This is something we are digging in more, again, for more cases to be able to really see if that's really the case or if it was just for this particular case. Tropical cyclone, which you know well, Irma, and these are actually runs which were done in the InSight program on Summit. We have an ongoing we had ongoing projects with Summit. As you may have known, we have done several simulations at 1.4 kilometers since a few years. Nisvedi had done this pioneer simulation at 1.4 kilometers for a few months that you might have seen already 4 years ago. Now we've looked in a more systematic way for tropical cyclones. We chose different tropical cyclones, and we looked at the impact of both atmospheric and oceanic resolution. I'm not going to go into too much details here, but it's really to show how the IFS behaves from 9 to 1.5 kilometers, and really the big jump is from 9 to 4.5 in this case, although for the waves, so again, you have the wind at the top and the waves at the bottom. For the waves, you really see a benefit in the extremes. As you go to the highest resolutions, the extremes are better captured. And the idea is to do more and more of these cases as well in destination Earth, to go towards 1.5 kilometers, as we can start to be able to run the codes on the EuroHP supercomputers. The second component of the extremes DT, it's an on-demand component. This is an activity we procured. So this is not, we don't do this at ECMWF, we manage this. And we had a competitive tender, which was won by a very strong consortium led by Meteo France, where many countries that you can see here from the Accord consortium. This is a numerical weather prediction consortium in Europe, which runs limited area models. They won, and they are going to develop flexible and scalable workflows for the short-range predictions of extreme events at sub-kilometer scale that are configurable and operable on demand, and it builds really on their Accord prediction systems together with selected impact sector models. And what is the idea here? The idea is to have the capability in Europe today, as I'm sure it's the case over the US as well. Different centers run on different domains that you can see here at the top, right? There are these fixed domains for the different countries. And the idea is to develop the technical capability to be able to follow a storm, for example. Today, the domains are fixed, so you need to run on this particular domain if there is a storm, and then you run on all of them, and then you see how the storm evolves. In Destination Earth, what the consortium has proposed is to develop, for example, the technical capability to run Accord as a storm evolves, for example, from Spain towards Norway, to run with imbricated domains, which ultimately will be forced with the global extremes DT. For now, it's forced with the IFS as lateral boundary conditions, the operational model. but really to have this zoom at sub-kilometer scale following the storm, or to have a capability to zoom in at higher and higher resolution if there is, for example, a pollution event, and at the highest resolution to couple the air quality models, for example, which today operate at 2-3 kilometers in Europe, and the idea is to bring them as well to sub-kilometer scale. So this is the on-demand, the extreme DT, which focuses on timescales of a few days ahead. Then there is the climate DT. It started a little bit later. It only kicked off towards November. It was also an activity which was procured, and the consortium which won, which I'll talk a bit about that in a minute, proposes to do multi-decadal global and storm and eddy resolving numerical simulations to develop this simulation capability at these scales with timely delivery for climate information for policy adaptation. Again, having use cases for impact sectors from water, energy, food, and health, and working with these users very strongly from the start. And the idea is to provide collocated climate and impact sector information really on scales where the impacts of climate change and extreme events are felt. And you can see here the jump in scales, which is one of the new aspects, which is going from the scales of hundreds of kilometers in, for example, in IPCC today towards the storm and eddy resolving simulations. You see again a beautiful simulation from NextGEMS at 4.5 kilometers. But that's only one part. To me, the really novel part is, and if we manage to do that, I think we would advance our capabilities quite a lot, is this data streaming, that the applications can be embedded in the workflow of the climate twin and can listen to the stream of data as they are produced and tailor the information which is coming out of the twins to their needs. So the climate twin is delivered by a consortium led by the IT Center for Science in Finland, with a strong involvement from the Alfred Wegener Institute and Max Planck Institute, and the Deutsche Wetterdienst in Germany, from the Barcelona supercomputing centers, but also from many other partners institutes in Italy, Spain, Belgium, and Finland. The two models are which are being developed at the moment in this Horizon Europe. It's a research program, research funding in Europe, which gives different research projects, and it's a really nice marriage of the investment in the digital program in Europe, which is Destination Earth, and the research program, which is what we call Horizon Europe, which comes together to advance the prediction capabilities. So the two models in NextGEMS are our IFS, which we are developing at ECMWF, coupled with two ocean models, NEMO, that's what we use today in operations, and FESOM, which is developed by, which is a final volume module, which is developed a final volume method we developed at the Alfred Wegener Institute. And the second model is ICON, which is developed jointly by the Max Planck Institute and the German Weather Service. Now, a bit more about NextGEMS and its storm and eddy resolving models. NextGEMS, it's how does it work? It works a bit like in NWP. We had this idea of trying to develop on a very fast track to see how fast we can get these prototype models at storm and eddy resolving scales with resolutions of the order of 2 to 5 kilometers, both in the ocean, atmosphere, sea ice, land, basically in all the components of the Earth system. So we started this in September 21, and we run in cycles. We run what we call by cycle is basically that we run the model for a few months. Then we come together in a hackathon. We had the first one in October 21 in Berlin. Then we discover the flows, we go home, we try to fix some of the flows, we run the model at higher resolution longer, we come together again in a second hackathon, we had that as well. Now we are kind of here in the project where we are getting ready for the third hackathon. And then at one point this summer, we'll say, okay, we hope that our models are more or less ready for production runs. And then we'll try to do one-off 30-year run just to see how it looks like at these simulations at these scales for the first time with kilometer scale in the ocean and the atmosphere. So what we have been doing so far, and there is a bit of detail here, but basically our longest and highest resolution simulation with the IFS was 3 kilometers in the atmosphere and 4 to 13 kilometers on average, about 5-6 kilometers with FESOM for 8 months. And we did a few simulations of 1 year with 4.5 atmosphere, and this FESOM grid icon has done several years at 5 kilometers in the ocean and the atmosphere, and a simulation of a few months as well at 2.5 in the ocean and the atmosphere as well. How do the simulations look? Well, they look pretty, that's sure, but there are also problems, as I'm going to show you. These are just a few images again from the sea ice cracks from FESOM, the wind gusts, which look absolutely stunning. You can see here only the wind gusts are plotted, and you can really see the imprint of the mountains on the wind gusts. But you also see the imprint of the sea ice cracks on the 2-meter temperature, the evaporation, and the sea ice concentration, obviously. So we see features which look realistic. It's another question of how can we verify these are actually realistic, in particular for the sea ice. But we also see a lot of flaws, because of course we are entering in new territories, and we should have known this, but we maybe did, but when we went to but then we thought it doesn't matter for NWP actually, and in retrospect it's a mistake. So we went to the first hackathon in Berlin, and then the participants to the hackathon, they looked at the IFS and icon, and the first thing they looked, because they said this have to be good climate models, let's look at the water and energy imbalance. And what they saw in our first 75-day simulation and 4.5 kilometers, where we had turned the deep convection off, there was an imbalance of 10% in water, and there was a 6.5% in watts per square meter imbalance in energy. In our 9-kilometer operational configuration with the deep convection on, that's what we use every day for daily forecasts, we still had a water imbalance of 5%, and we had an energy imbalance of about 2 watts. Well, then we went home and said, well, what is it? And then, of course, our dynamics experts knew that. We knew that the semi-Lagrangian is non-conserving. But as I said, we always thought it doesn't really matter that much for NWP, obviously wrongly. So we fixed that by activating trace mass fixes for all moist species, and by fixing a few bugs. We are now much better. We have an imbalance in water of about 0.1%. We have an imbalance in energy of less than 1 watt. It would be good to bring that further down, but already it's an improvement. So the model development cycle in NextGEMS was working. Then we said, okay, what does it do for NWP? And surprise, we have, I don't know, for those of you who are familiar with NWP scores, this is the way we, when we have a model development, how we look at its impact on forecast kill across ranges. At ECMWF, we are using the same physics across all time ranges. And we are trying to do that now as well for the climate range. So we put these mass fixers, all these changes for the water in our forecasting system, and we ran our ensemble, our new future version of the ensemble at 9 kilometers with these changes only. And this is a typical, what we call scorecard. What you see here is the geopotential, temperature, wind, relative humidity, 2-meter temperature, etc., verify against the analysis. And you see the North Hemisphere, South Hemisphere tropics, the CRPS, and these are the little cubes, squares, there are the forecast days. And what you see is mainly blue everywhere means improvement. There are a few things which are degraded, but this is quite a blue positive scorecard. And if you would be able to click here, you can't, but if you click on these boxes, it shows you the actual change. So this is about 2% in the mean absolute error for precipitation from day 1 to day 15. It doesn't only do that in the medium range weather forecast, it does this in monthly forecast as well. This is a bit lower resolution here, about 36 kilometers. And again, the triangles, when they are blue and pointing upwards, it's an improvement. So this is quite impressive, actually. And the reason I'm showing this is because, to me, this is one of the success stories. Many people say that maybe, that will take a while until the storm eddy resolving models, we take something out of them, they are ready for operational use. But the point is, by pushing the models in different ways to their extremes, we find things that through which we improve the systems, even at the current resolutions and in the current operational applications. And this is one of the success stories of NextGEMS. And this model cycle, this model change actually was the fastest operational implementation that I can remember in my 12 years at TCMWF, and this is about to be put in operations now. But this is not the only challenge, and I'm not going to read all this. I'm just going to brush around the headlines that if we want to develop digital twins, we really have a lot of challenges in both computing science, technology, and I mentioned this before, the science computing co-design, the performance portability, the data-centric workflows, the supercomputing cloud, and bringing ML, AI in, that's one thing. But then there are the pure science challenges as well in terms of Earth system modeling. Beyond these prototype storm and error resolving models that we are for now playing with and developing NextGEMS, and beyond the pretty pictures, we really need to bring this to fully operational systems. And for that, there are many, many science challenges. I'll go in a few of them in my last 3 slides. There are challenges with the integration and co-design with impact sector modeling in many ways. There are challenges with uncertainty. Everything I talked about, as you notice, and I know that's a default, of course, I'm very much for ensembles. For now, we first need to develop the systems and these resolutions in a deterministic mode, but we also need to think about uncertainty representation and be ready to run ensembles when we can afford them. But how you represent uncertainty in the scales may not be the same way you represent uncertainty at the current scales. There's science there as well. There is the whole ML AI approaches, and we've all seen the flurry of papers, and in particular the shock that the GraphCast paper delivered. We are talking 60% or 70 to maybe 90% of the coffee breaks at TCMWF about the GraphCast paper. Tells you something. So there is the whole the whole way of how do we bring machine learning in more in our systems, or both not only for emulation but also for data compression, for uncertainty quantification. There is the verification aspect. At this, as you go to kilometer scale, RMS is not enough. We need new ways of verifying, and we need new ways of verifying as well the climate models as they go to these higher resolutions. There is the whole data, the whole initialization issue at weather scales, but also use of observations at climate scale, also for initialization, but also for verification. And the observation information extraction and going towards new types of observations, about data assimilation methodologies at kilometer scale. So there's a whole plethora of challenges. I will focus just on 2 or 3, which are close to my heart because I've done physics for my entire career, mostly, even if I've touched upon every aspect of NWP. But I'll end with 3 slides on challenges in terms of systematic errors, and why I come back to this idea, why I think that developing both the weather and climate together with the same systems at the same resolution is a benefit. The first example is precipitation in the tropics and precipitation extremes. What you can see here on the right, if you look at the right first, you can see the zonal mean precipitation in black are the observations, it's image, GPM. The different lines are different runs from NextGEMS. Basically, our 9 kilometer with the deep convection on, it's the closest to the observations. If you run the 4 kilometer with the deep convection off, you have this huge peak here over the Pacific. And this is in the first 10 days. This is a simulation that you start on the 20th of January, 2020, when there was the Eureka campaign, and you run 10 days and you look at the bias. If you let the model run freely for 12 months until December, you do the precipitation plot, it looks almost the same. Well, in this case, the 9 kilometer also look worse, but also this peak of precipitation in the 4.5 kilometer, the point is you see it after 4 days. You don't need to run 10 years, 1 year to see a bias. You can very quickly see this bias is developing on a very short time scale. Then it's very easy to try to figure out the source of systematic errors and to improve the model. It's easy to do that if you don't need to wait for a few days or weeks to run your simulation. And even more beautiful, you see this from 1 day. So this is 1 day of simulation on one of the summit simulations. You see lots of lines here, but the black is the observations. The light blue is the 4.5 kilometer with deep convection off. The 9 kilometer is the operational deep convection on. 4 with deep convection on is the green here. So you can see that the parameterized runs, there is too little extreme precipitation. There is too much extreme precipitation if you turn the deep convection off. But the good news is that the 1 kilometer is much closer to the observation, and there is a little bit of difference between red and yellow here, whether you run with the deep convection on or off. So even at that scale, there is a sensitivity to the representation of moist physics, as you would expect. But the point is, you see this from a 1 day simulation. And it's exactly the same as you see at longer timescales. And we are working to try to understand where this bias is coming from and how much convection should remain parameterized at these scales. The second reason is if you run the model both at long time scales and at short time scales in weather mode, and you look at it with the huge magnifying glass, which the NWP scores are, well, you can say you're not very happy, but in the meantime, you're very happy because you figure out early enough the problems. So this is the first scorecard ever we ran 4.5 versus 9 kilometer for winter season for 2 months. These are, again, these little boxes here. The top panel is against analysis. The bottom panels, it's against observations. 4 minus 9, where it's red, it's bad. So at the moment, the 4.5, it's much worse than the 9 kilometer. Good news is that we've understood part of the problems. This is the North Hemisphere, that's where it's the worst. Then is the South Hemisphere, and this is the tropics. Where is it coming from? In the North Hemisphere, you can see that if you look at the cross section here, this is the geopotential height, root mean square error, 4.5 minus 9, 3 days ahead. You can see red throughout the troposphere, and if you do a cross section at 100 hectopascal, you can see the jet here. So the problem is mainly due to the breaking of gravity waves above the Himalayas, and we detected that most of it was because the time step we chose initially was too long. The time step was too long, and the mean orography was not constructed properly. I mean, it was not constructed properly, whatever properly means. The point is there was too much small scale in the orography at 4 kilometer. It was producing small gravity waves, which are breaking unrealistically in the jet. They were slowing the jet, and that was even worse when the time step was not short enough. Now with a shorter time step, a new mean orography, this goes completely away, but the lower part here doesn't go away, and the tropics deterioration doesn't go away, and that we figure out in the meantime is due to a sensitivity of the time step of the moist physics. Of course, many people, when I showed this, they said, yeah, but hold on a second, you are going at higher resolution, you verify against the 9 kilometer analysis, and besides, you look at RMS. Of course, you'll get red scores, a red scorecard, a bad scorecard. Yes, I know we need to also look at other metrics, and we are developing metrics as well. I mean, adopting methods which we have been using for many years in the regional NWP community, like FSS, the fractional skill score. And that's what I was saying, that there is a work on the verification side as well of how we verify the systems. And finally, the climate twin. How is the climate twin doing? And there again, I want to show you first that again, if you look just on the right-hand side for the beginning, if you look at the shortwave TOA, the top of the atmosphere bias, and IFS at 9 kilometer, this is after 7 months of integration in the NextGEMS runs. And you can see red and blue. That's not the point now. There is too much radiation at TOA, so the clouds are too reflective. But the good news is, in a way, that you see most of it after 5 days. So these are 5-day forecasts, also with the IFS for July 2021, and you can see the patterns are largely similar. So again, to tune the radiation balance, you can largely look at short integration. That's enough. Now, how are our NextGEMS models doing in terms of drifts, which is an important point for climate? These are preliminary. These were the runs in cycle 2. We hope the cycle 3 is better. This is the Gregory plots. That's the top of the atmosphere in balance, global average versus the surface temperature global average. The different runs are the different colors. The gray here, it's Ceres and ERA 5. So it should be kind of here. It should slowly drift towards a warmer state. You can see the IFS, it has a positive radiation imbalance and it's drifting warmer. It's not too far from the observations, but it's kind of, after the first year, it's maybe half of a degree, 1 degree too warm. While 2 of the icon runs, they have different flavors of icon, but you can see that one is really drifting badly cold, and one it's a bit more stable. And this is because they have an energy leak, which is quite important, and which they are trying to fix. But anyway, if the point is that we have many challenges to go towards these systems and take advantage of their of the benefits that we expect, both in representing better the extremes, because of a better representation of better resolving processes, and hopefully, and I think that's the large prize, and I would be interested to think what you think, and if what's the evidence in running global kilometer scale simulations with MPAS, for example, of how do we demonstrate that better resolving the small scales affect the large scales and improve the large scale circulation, which we hope that is the big price of running kilometer scale global models. And that, for now, given the biases we have, I think it's quite hard for now. But anyway, if we solve all these, then hopefully we will arrive towards digital twins of the Earth. And this is just a beautiful picture from a GOES satellite image and an IFS simulation at 2.5 kilometers. And that's all I had. Thank you.
Right. Thanks so much, Irina. Very interesting presentation. We have time now for a few questions, which will be coming in on the Slido system. So a moment for that to be activated.
So.
We have questions. Let's see a cursor moving. While waiting for that, I'll ask you a question. So
Sure.
if you could make like these 30-year forecasts every 6 months, say, so that it seems like you'd have a pretty good setup to do a global predictability experiment by simply taking the differences between those two forecasts at 10 years, for example.
Yes, that could be done. What is clear is that we can't save all the variables. So that's this idea of streaming, that the applications would save what they need. So they would need to listen. So there will be some data which will be saved, but in the data lake, but I'm not sure what you need. So you would need to decide, or one would need to decide in advance what is needed to look, what you need to look at, and try to save those fields. Because the idea is that this data is produced, the applications take what they need. There is a little bit, a few key variables which are saved in order to verify the quality, etc. But then the data is flushed out, right? Because you can't save possibly this amount of data.
Right. I mean, something like typical predictability things are disturbance kinetic energy. U1 minus U2 integrated.
Yeah.
So
that could be the, so the idea is that for everything like that, it would be needed to be coded in the model, which can be, and then saved. But yeah, yes, yeah, that's an interesting question.
Andy, if you have your hand up, if you'd like to unmute, go ahead and ask your question.
I think Judith had a comment in the chat first before I raised my hand.
Yes, I was wondering if you could tell us a bit more about the interactive user-driven aspect of Destination Earth.
I can tell you that that will come later, right? As I was saying, this is the vision, that's the 10-year vision. For now, of course, there are no interactive user-driven aspects. The idea would be that at some point in the future, that capability will be developed. How exactly, these are questions we are working on with the European Commission, with ESA, EUMETSAT. Who are the users, who can drive what, and how exactly this will work. So I think that's all I can say. The idea is to go there. How exactly how interactive will be, how who will be the user, who will be. It's not imaginable that everybody can run a climate twin, right? There will be different levels of interactivity, but the interactivity will be more in this, it'll be mostly probably in the sense of a user running its own application to collect data from the twin, or to add its layer of a model and blend it with data coming out from the twin, or things like that. That's how I see it. But to be seen.
Okay. Yeah, thanks. Thanks from Judith. So Andy, did you have a question?
Yeah, I really like what you're doing with trying to develop the model on shorter timescales when you see this biases emerging early on. And I can see that this will save you a lot of computational resources. Can you also run the model on regional domains? Because like the biases that you showed, for example, the stratocumulus cloud lake regions,
Yeah, no,
you probably could tackle those in a regional domain as well and
but
save.
not the IFS. The IFS we cannot run it.
But I think ICANN could.
ICANN
Are they doing this?
No.
No. Okay.
No, they are running globally. The good thing is the radiation balance, and I didn't include this because it's too early days, but Tobias Becker, who was working with us at TCMWF, he has done a fantastic job really running a 12-day simulation and tuning the radiative global mean radiation balance to zero. Basically, it looks unbelievably good. We have to see now how it looks. So he has done it for a few dates, and then he has done it consistently for a season, and it still looks good. Now we have to run the real simulation of 1 year to see how it behaves and how it looks regionally. But I think we found we always knew the knobs, right? You know the knobs to tune the radiation balance. But I'm very happy that it seems that with a 1-day simulation, you can almost tune the balance, the radiation balance. So you don't need to, because that was the big fear, right? How do you tune these models? How expensive it will be to tune these models? But if you can do that with 1-day simulations spread out throughout the year, 4 or 5 of them, one per season. Let's see. I think there is some hope.
Thank you.
Okay, I don't see any other questions in the Slido or in the chat. So I think with that, Well, thank you, Irina, for giving us this seminar. Thank you for staying up late to
Thank you. It's not that late yet. It's only 10 o'clock.
I'm taking your evening to do this.
Thank you very much for the invitation.
Okay. Good night. Bye.
Thank you. Bye.